So, I'm going to talk to you about materials informatics. I don't know why it's doing the automated stuff. Let's see. I didn't plan for any animation. So, if you're curious about what this is, there are a bunch of websites, and of course, I know you don't have access to the slides, but if anybody is interested, send me an email, and I'll send you all the links. Okay? And this is background information, if you're curious. Because how many of you know what Materials Genome Initiative is? Nobody knows that. Okay, good. So I'll say something. I have a slide. I'll say something. It's a national strategic initiative. In fact, it's the very first one in the entire history of the United States that materials made it into a national strategic initiative. So materials has never been a national strategic initiative in the US, and this is the first one. So it's exciting. Some of you heard about ICME, or right? So ICME is happened before MGI. The difference between them is ICME is done by what we call as national academies. So they really don't have any money, they just talk, and that's what that is. MGI is more the federal agency, so they can actually put money down and behind what they say. So that's the main difference, I think, in some sense. That's the official website for MGI, www.mgi.gov. It's a government website. This is the original announcement, I guess. No, it's not the original. The first one is the original announcement. This one is an update. So this is the updated one. So next version of it. And again, I'll send you links to this. A lot of the talk, you asked me if I was ever recorded. So a previous version of this was recorded, and it's on Coursera. If you're aware, do you know what Coursera is? It's a free, basically it's a free MOOC. So you don't have to pay anything. It's completely free, and it's available just in case you want to go through that. And a lot of what I'm going to show you is also in a book, and that's the book. So I'm happy to share this information. I don't know why this is doing this. So well, that's the easy solution. So what I'm going to do today these topics. I'm going to talk about the mathematical theory of microstructures. Everybody has seen microstructures, right? Everybody here knows what a microstructure is? Okay. So you've seen a microstructure. If I showed you one, you would know whether you will recognize and say, that's a microstructure. But how do you mathematically represent it? That's a totally different problem statement. So I'll talk about that. And once we define that, it will naturally lead to what are called as spatial statistics or endpoint spatial correlations. Then we'll realize that then the number of statistics is very large, so you cannot do anything useful with it. So you have to do something, and that's the dimensionality reduction part. So those are the first 3 bullets, and my plan is to use the first 1.5 hours to do the first 3 bullets. And then once we have a reduced order representation, I'll show you how to use it to produce structure property linkages and process structure linkages. So those are the last 2. So I'm hoping to basically get here at the break and then do the second half. Okay, so that's the plan. Okay, so MGI. So MGI is Materials Genome Initiative, and ICME is here, down here. So ICME. So if you look at how materials are designed and introduced into commercial technologies, it's a very long process. It has multiple stages, and it's incredibly long. And typically, across all industry and all applications, people report about 15 to 20 years. And that's usually a lot of money and a lot of time. And basically, ICME as well as MGI talk about speeding up. How do you get there at half the cost, half the time, that kind of stuff. So we want to be able to get there fast and cheap. Okay. So as you can imagine, this has huge economic implications, right? I mean, if you can make better materials and put them into technology, who doesn't want it, right? Everybody wants it. And if you can do it cheap, no, everybody wants it, right? So how do you do that? And notionally, what you see here in this picture is this is just a notional picture. Again, there are no numbers on any axis, right? So nobody is claiming anything. And essentially, what they're saying is, okay, let's see. Can you see my pointer? Yeah. So what we are saying is currently this is the rate at which we are doing things in a sequential process. And the idea here is that potentially one can go at a higher rate if you do this entire workflow in a more concurrent workflow. So you don't want to do this in a serial sequential way, and you want to do it in a more concurrent way. And the question really is that even possible? Right? I mean, again, MGI says, wouldn't it be nice to do that, but it doesn't say how to do it. That's for us to figure out. And the question really is it even possible? And this is just a marketing thing where you're saying, essentially, if you are able to do that, it affects pretty much everything you can think of, from energy to national security to welfare to next generation workforce. So there's basically, it affects everything, essentially, right? And the only other idea that kind of made it into this symbol for MGI is the idea that in the last 2 or 3 decades, people have been using experimental tools and computational tools to do this problem. I mean, I would still say it's mostly experimental. This entire workflow is mostly experimental, but models have started getting in there. 10, 20 years, models have started getting in there. And really, this picture says it's not enough. You actually need to have another leg or a foundation, and that foundation is data science or digital data. And what it recognizes is that there is something missing there, especially this was done about 5 years back. ICME was 2008, I think, and this is about 2012 or so. So in ICME, there is still discussion of digital data, but it doesn't actually come out in a very sharp way. And what MGI does is it brings it out very sharply and says you better pay attention to digital sciences or data sciences if you want to be able to get there. So that's the notional idea. So now what does it really mean? Now how do we, as material scientists, how do we get there? The first thing that we have to recognize is that in material science, we are out here. We are looking at images like the ones at the top. And we are supposed to get knowledge out of it. There's a lot of data. So in terminology, you say that's data, right? And data comes in at different scales. If you do TEM, you can see atoms or columns of atoms. You can see dislocations. You can see microstructures. You can see grains. You can see transformation plates, phase transformations, and so on and so forth. So that's what we typically do in material science. And we are trying to get information that is going to drive or is useful or valuable to people who are doing design and manufacturing. Right? So we need to find a way to communicate with them. Obviously, if you start talking to design and manufacturing people and talk about dislocations or grains, I don't think they have any interest, and they're saying, so how is that connected to me? Tell me something useful to me. And of course, in material science, we have known that for a while. That's not a new revelation of any kind. And what we have always said is that material science, the knowledge in material science can be captured in process structure property linkages, PSP linkages, and we should be able to communicate. But the communication has always been difficult. It's not that easy. It has not been easy, mainly because the structure, there is no single definition of structure, right? All of these are structures at different length scales, and we need to find a way to quantify that, and we need to be able to package them into quantitative linkages. Then that I can then transfer to design and manufacturing experts. That has always been difficult. Okay, and the question now is, can we do better? Okay. Now, the vision, the rest of the 3 hours we'll go into details of how we are going to do that, at least one way of doing it. The vision is, if we are successful in what we are doing, then we can imagine that we are going to do material science in a knowledge-driven framework. What it really means is, For example, if you are here at this scale, you do a lot of simulation. Let's say you do 1,000 simulations at that scale, because today you can, right? I mean, before maybe not, but today you can. You can do literally many of them, because you can script it, you can send it to a cluster, and boom, you'll get the answers, right? So if you do thousands of these simulations at this scale, how do I extract some knowledge systems? So these are symbols for knowledge systems. How do I extract knowledge systems from those 1,000 simulations, right? So the definition of a knowledge system, I guess I didn't put that in, is that if I have 1,000 simulations and you change something in the inputs and give me a new set of inputs, if I have a knowledge system, I shouldn't have to go and run the simulation again. I should learn from the 1,000 simulations, and then if you give me a new set of inputs, I should be able to answer it just like that, without actually going anywhere. That's the definition of a knowledge. In other words, knowledge has to be transferable. I have to learn something from those 1,000 simulations so that I can tell you something about some new simulation that you haven't exposed me to. And the question is, what is transferable? How do I formulate this in a way that is transferable? Okay? But if it happens, then we can do multi-scale modeling very easy, right? While I'm on this slide, I want to point out that basically this is scale bridging. The difference is that we want to do it by knowledge systems, but there are two directions. There is a direction in which you're going up, which in the composite theory we call it homogenization. So basically when you go from here to here, I only want to know effective values. I don't really care about all the details. I only want to know the effective values. When I go up, I only want effective values. But sometimes I have to come back. On the way back, I want localization, where I'm going to change something here. I instantly want to know all the changes that happen there without actually doing the calculation, right? That's the localization part. So when I build knowledge systems, I want to build them both in the homogenization direction and in the localization direction. Of course, building them in the localization direction is incredibly more complicated, but I'm hoping to show you that there is a way to do it in a very systematic way. And in fact, the framework in which we do is actually exactly the same. We use the same framework going up and coming down. It's just that the effort involved is much higher. Okay? You have to work much harder to get to the way down, obviously, right? It makes sense. Hopefully it makes sense. The other difference between this and what has been happening in multi-scale modeling before is that people do multi-scale modeling of this kind, but they're doing it concurrently. In other words, they're doing this and this simultaneously, where you do a simulation here and then you send it out to do calculation somewhere else and then bring it back. I don't want to do that, right? Because that slows me down. I want to build these knowledge systems completely independently, right? So my vision is that we're continuously building this, and then when I do the actual simulation, I just come to the knowledge system, get the best available answer at that point in time, and then go back. Okay? So the example I often give is, I say it's almost like how Google works, right? When you type something in Google and you search for something, Google is not then going and finding all the websites. It already has pre-computed a list of all the websites that it thinks. It is anticipating what you're asking, and it gives you the best possible answer it can based on what it has in its database. So I want to do similar kind of things in multi-scale for the obvious reasons. I hope it's clear as to why we want to do this, and it's what it is. That's the general idea. Because of this particular way of doing it, one has to pay a lot of attention to uncertainty, right? Because same way in Google, right? I don't know exactly what you're going to ask. I'm going to guess, and I'm going to be ready for you. But I cannot be exactly right all the time, right? So I have to pay a lot of attention to uncertainty. And so the game becomes a question of managing uncertainty. It is basically, at the end of the day, you're saying, I want to be able to manage uncertainty the best way possible. Okay? So it's a very different paradigm in how we want to do multi-scale modeling. Okay? Any questions on this? And of course, I mean, the automation part is that we just want to do it very fast, right? And we want to do a lot of this, right? So that's the general idea. So as we go along, maybe it will help you a little bit more. I'll try to show you what we do. So this is a visual, again, still a vision picture, so I'm not going into details yet. of how we envision the entire thing to happen is that we are still interested in PSP linkages. So this is what we are calling as materials knowledge, is PSP linkages. These are what we are calling as materials knowledge. If you think about it, the sources, information sources for materials knowledge is mostly either experiments or simulations, right? Those are the only places you can get information so that you can do PSP linkages. But they come with different kinds of attributes. Usually when you do experiments, you only have a limited number of samples. You don't have infinite number of samples. Typically, when you do experiments, you don't know physics, so you're trying to find the physics. You want to understand how that behaves. Whereas when you do simulations, it's the other way around. In a simulation, typically you select a particular structure, you assign a certain structure, and then you impose physics, known physics. That what you're imposing may have nothing to do with reality. That's irrelevant to the numerical simulation, right? You're taking a structure, you're imposing a physics, and it says this is the answer for those inputs. That's all a model does. So models are good in certain other ways. They're for selected physics and material structures. Because most of the models are numerical, like finite elements, phase field models, they generally give you forward information. They cannot give you inverse information. In other words, in a finite element kind of a sense, I cannot give you the stress field in a 3D RV microstructure and say, go tell me what the inputs are. Go tell me the loading conditions, right? So the invertibility is not there. But you can generate a lot of data. And these days, we can generate a lot of data experiments too. The ability to generate data has significantly increased, but it's nowhere near what you can generate with models. With models, you can generate a huge amount of data today very, very fast. So this is all about generating knowledge. And the question then is, how are you using the knowledge? So I guess I can do this. So this is all about generating knowledge. So this part is generating knowledge. Then the question is, how do you use it? And the best way to use the knowledge is, at least from a statistical learning point of view, the issue is that we admit that the PSP linkages are only known to a certain level of uncertainty. We'll never know them exactly, right? So we have given up on that. We will postulate or formulate and say that we'll never know them exactly. Now the question is, if you decide that they're not good enough and you want some more, what are you going to do? How are you going to decide what new experiments to do, what new simulations to do? If you give me a choice of 10 different things you could have done, can I give you guidance on saying you should be doing this and not that? That's another question that one can formulate, right? And the advantage of doing that in a cycle like this is one can think of pretty much robotic execution of science, right? So I don't need, at least in vision, I can basically do science using completely automated workflows, right? So every piece of this can be robotized, if that makes any sense to you. Okay. So the question we are asking is that even feasible? So can we generate this materials knowledge in a completely automated way? We are nowhere near there. Okay. I don't want you to think that we can do this right now, but can we start thinking like that? Can we start doing it this way? Because that's the slow part, right? When it takes 15 to 25 years, it's because we are very slow in getting things done. So if you want to speed up, there is absolutely no other, at least in our mind, there's absolutely no other way. I mean, the only other way is to increase the number of people working on it. But that again is not very practical, right? So that's the argument. So now the question then is, how do you do it? This is what I'll go through for the rest of the 3 hours. So there are these what we call as templated workflows. We build this workflow. So the blue boxes are the main modules. I'll be spending a lot more time on these two until the break, and then I'll show you a little bit of this. But these are complicated. They usually take a long time. I teach an entire class, 15 weeks, to go through this entire thing. So it takes a long time. And the white boxes are options. Basically, the vision is that all of these can be programmed, and the computer can be made. We can make the computer smart enough that at some point the computer will know what to pick in each option. You actually don't even have to tell the computer what to do, right? So again, that's the vision. right? Again, as I said, we want to automate the entire thing. We want to be able to get materials knowledge in automated workflows. So the reason I put this up is all of these codes we share with the entire world, so we don't keep anything secret. All our code, I mean, the latest work we do in the last 2 or 3 years is probably not there, but anything up to a few years is here, and so you can download it, do whatever you like. It's a GitHub repository, so you can take any code. You don't have to tell us what you do with it. You can do anything you want. If you decide to share it, you can send it back, and we'll it's GitHub. Does everyone know how GitHub works? Okay, so it's a GitHub repository, and this particular website has like a manual and things like that. So there is some theory part. There are definitely examples. So if you want to run through the examples, so that you can see what we get when we run the same code, right? Because sometimes just because I shared the code doesn't mean you'll get exactly the same answer as I get, right? So there are some examples there. There are input files, output files. Feel free to run them. Do whatever you like. So that's supposed to be a community effort. It's funded by NIST. So, but we run it, but it's basically funded by NIST. Okay. So that's my overall introduction. If you have no questions, I'll jump into details. Go.
So knowledge or experiments are usually carried out at different places. So in universities and in research institutions, how do you synchronize actually the knowledge? So because you have to feed your system with the basic data, right?
Right.
So how do you do that, or how can that be done then automatically?
So which part of it? Because I need to understand your question a little better, because some of it has to do with data translator. In other words, one machine produces a particular data format and another machine produces another format. Those are just, in our opinion, that's just a translator, right? So the cost of doing that is, it's a one-time cost. If you have to write 10,000 translators, 1,000,000 translators, it's trivial. Compared to what we are talking about changing the world, right? Doing 10,000 or 1,000,000 translators is no big deal, right? So that's almost. The other part of it is, if I give you an SEM picture from one vendor and an SEM picture from another vendor, the file automatically doesn't tell you what you're reading, right? Because so that's what you call as metadata or metadata schema. And so the question is, how do I do that, right? If I know that the file was generated by, say, a test scan SEM, and there are enough parameters there, how does the computer interpret that and understand what it is looking at? So you call that metadata schemas. And so NIST is doing a huge repository of metadata schema. It's called MDCS, Materials Data Curation System. So once people start using them and feeding them, the data is self-explanatory, right? So again, so we're not doing all the pieces of it. We are doing some pieces of it, but it is coordinated, and other organizations in the US are doing parts of it. Okay, so I don't know exactly what. So then the other question is, what is knowledge, and how does knowledge combine? In other words, if you get the same Excel sheet, inputs and outputs, and you give it to two people and say, go build a model, they are very not likely to come up with the same model, because I'm not telling them fit a straight line or fit a power law, fit a stress strain. I'm not telling them anything. Then they're not likely to come up with the same model, right? That's the part we can parameterize. So we actually believe we can parameterize the heck out of any model, right? So in other words, then if you give me a model and they give me another model for the same data, and I have enough information about the error and error distribution, I can make a decision on which model I like, and I can also make a decision on which model, and even if I have the data, I can take your data and put it on his model. I can take his data, put it on your model, and so that part is included in our workflows. So it's a question of which part of it. It's a complicated problem, and we think we're addressing different pieces of it. I mean, overall, somebody is addressing every piece of it. We are addressing parts of it. Okay.
So one question: so if you consider one material, let's say crystalline solid, and one material, the same material, but it had some pre-treatments, heat treatments, line strengthening, whatever. So you would have to create a database for each of these initial treatments, for each temperature, for each phase composition, for each.
So the way we think of it is that when you do a heat treat, that's what you mean by process structure property linkages, right? So let me see if I can write something. Is there something to write? You see it somewhere? Red box. Ah. Oh, this is real chalk. Oh, this one. I see. So people still use chalk? Because I don't want to mix that up. So, so process structure property, right? So based on what you said, Julian, all the heat treatment and everything, heat treatments and all the stuff comes in here, right? And this is structure. So if you have aging, if you have more solid solution, less solid solution, segregation to grain boundaries, porosity, vacancies. In fact, a lot of in mechanical properties, when we talk about structure, we are simply talking mostly about defect distributions. We're really not even talking about the structure itself, atomic structure, because mechanical properties are a lot more sensitive to defects and grain bound. Everything is included in there. So in our definition, all of that goes into here. So when you do a heat treatment, the structure changes. But the model that I have for structure property linkage, the model itself should not depend on that. You should be able to put any structure you want, and I should be able to get a property.
Databases just to be large enough to capture.
Right. So the models, very good point. So historically, people have been building these models. These are not that nobody has built the models, right? In fact, they're very popular. The most important structure property linkage in metals is, does anyone know? What is the most important structure property linkage? Important from an economic point of view. People made a ton of money on that historically. Hall-Petch relationship, right? Basically, right? So strength is equal to some constant plus kd to the minus half, right? Right? That's basically, that's the one that made incredible amount of money for metal industry, right? So, but it's only applicable in small windows, and you have to you have to get the constants all the time, and you have to reestablish. And anything you do, you have to change. So, applicability of that model is very, very low. So that's why everybody does Hall-Petch constants again and again and again. Every few years, everybody does that again and again and again, right? Because the structure part is not very clear. There is only one structure parameter. These are not independent of structure. Right? So this is not what we have in mind. We want to go well beyond that. Okay? Does it make sense? Okay. Again, we want universal models, but we're not going to get that either, right? At the other extreme, right? I want universal models. I would love to get them, but that's also not possible. So we just want a bigger windows of applicability. And eventually, hopefully, eventually, it will become universal at some point. Maybe not in my lifetime, but maybe in your lifetime. Okay. Okay. So, any other questions? Okay. So now we get into the first topic, which is mathematical representation of microstructures. So let's make sure that we define this better. Well, I mean, and terminology notation is very important, right? So if you don't get the notation right, the rest of my lecture will not make any sense. So better make sure the notation is right. So we think of length scales. So in a macro scale object, there is a length scale. And that's probably in a macro scale object, if you're doing macro scale finite elements, you have an integration point. And that integration point has some length scale associated with it. So that's a macro scale length scale, uppercase L. If I take that volume and expand it by many, many orders of magnitude in a microscope, you'll start seeing something like this. This length scale is still smaller than that L, right? So keep that in mind. This L is typically in most structural materials is at least in millimeters. You're talking about several millimeters. And this one is probably thousands of microns or hundreds of microns at least, right? So this is still lower than that. This is the length scale of what we call as the RVE length scale. So we are pretending that This is a representative, in this case area, but think of it as volume, because just think of a third dimension. But this is a representative volume in that, at that material point. If I go and close my eyes and pick a representative volume, that's what it looks like. And of course, at this scale, again there is another length scale, and this length scale now is in microns maybe. So this is much smaller. That little l is even smaller than this. Okay. So we think of these three length scales, and essentially they are important because constitutive models, homogenization, localization, constitutive models are defined at the two length scales, uppercase L and lowercase l. There is still heterogeneity. In other words, even at this lower length scale, I am pretending that the material inside that length L is homogeneous. But of course, it's not, right? If you go in and look at it, there are atoms, there are defects, there are dislocations, vacancies, everything you can think of. Then there is an assumption of statistical homogeneity. What it basically says is that if I take volumes of this length scale out of from that point, if I take multiple ones, they look almost identical. They don't look pixel by pixel, they are not identical, but the material content, the structure in there is identical, right? So that's what the statistical homogeneity means. So the microstructure is heterogeneous. So this is heterogeneous, but it has statistical homogeneity. Essentially what it means is that if I believe that this plate is made uniformly by the same process, then if I take a cube here, a cube here, a cube here, they have equivalent information, whatever that means, right? And that's important because that's what gives a separation of length scales. And yeah, so this is the statement. This is the statement I'm looking for. So this is significantly smaller than this, and this is smaller than that. Okay? So that entire assumption is called separation of length scales. Without that, there is no composite theory. Every composite theory that we know of makes that assumption. Then if you say, well, is it a good assumption? Maybe, maybe not. The problem is, yeah, there are many things we can think of where it doesn't apply. There are lots of examples where if you sit and think about it, you'll come up with examples where that's not true. But we don't have any other theory. This is the only theory we have. So, so even if it is not working, we still assume that and go ahead and move forward. Okay, so all composite theory, every composite theory makes that assumption. Okay. Now, I need a couple more statements, definitions. I'll talk about local states. Okay, a local state. So now I have to somehow define what is at this length scale, at this little l. I need to be able to tell you, is it copper, is it aluminum, is it polymer, is it something, right? I have to have a label, right? Because now I need to be able to mathematically describe that. So that's what I'm calling as a local state. So whatever I have taken the volume, broken it up into pieces like voxels, but in each voxel I have to put something in, right? And that's what we are calling as local state. How do you describe what you have? So at this point, we are going to be vague about it because it depends now. It's not very, and I'll show you some examples. So depending on the application, we have to do that. And this part, we haven't found a way to automate yet. So this part is pretty much human. At this point, this is human beings doing this. Okay. So we're saying local state is basically all the attributes needed to specify the local properties. So when I know the local state, I'm able to tell you all the properties like density, if I need density, if I need modulus, I need modulus, whatever else I need to define that. Right? That's local state. Local state space, mathematically the word space, anytime you add space next to anything, is just basically the set of all possibilities. Whether or not you have them in your particular problem, it doesn't matter. It's just the theoretical set of all possibilities. Okay? So local state space is by definition a fairly large set, because if you think of all possible local states, they're all included there. So you cannot define a local state that's not inside the local state space, because if you define it, then I have to add it by definition. Okay? So just those are definitions, just to give you an idea, just so that you have some idea what it looks like. For example, if I look at this kind of a microstructure, so I'm going back to this one. So there are two phases. In this particular case, there are two phases. So for something like that, I might decide the local state. To define the local state, I have to tell you what the phase identifier is. If I have an alpha beta microstructure, I'm telling you, oh, that's alpha, that's beta, right? And that's what this is. But sometimes it's not enough to say that. You actually have to tell me the composition of the alpha, for example, because alpha can come in multiple compositions. Titanium, alpha titanium, it only has limits. Anything in between is still alpha, right? So one has to define that, right? And this is the definition of space. So this is the variable itself. This is the set of all possible definitions of that. And the local state space then is simply all combinations of this, where this goes through all the phases of interest, and this variable goes through all the compositions of possible. So this is a fairly large set, right, basically. So any combination of phase and concentrate compositions is included in the local state space. Okay. Any questions on this? I'll show you one other example if you like, and this is polycrystal. So now, in addition to phase identifier and composition, every voxel here, I also decided that crystal orientation is important for me. So I added the orientation to the definition of the local state. So my local state now, every voxel has a phase identifier, a composition identifier, composition values. So this is an identifier. This is just a 1, 2, 3, 4, 5 kind of a thing. As long as I know 1 is always alpha, 2 is always beta, and so on and so forth. This is actual numbers, right? Between, you can define it as atomic percentages or weight percentages, whatever you like. And G is the orientation. And they all have ranges. So concentration has a range, orientation has a range. It's called a fundamental zone. So if you know what fundamental zones are, then you know what this is. So orientations cannot be anything they want. They have to be what are called as elements of SO3, right? So orientations have to be a part of SO3. And the difference between SO3 and this is simply that this accounts for symmetry. So cubic crystals have a much smaller space of range of possibilities than non-cubic crystals, for example, right, or hexagonal crystals. So all that is included in there. So that's the definition. Any questions on this? Right. I think each piece is not exactly 1, but it will be whatever it is, 0.6, 0.7, whatever it was. Right. So this particular case, I think the axis is just an axis. The voxel size is not. I don't remember now, but it's not exactly 1 by 1 by 1, but it's close to 1 by 1 by 1. It's something around 1 by 1 by 1. Okay. Yeah. So the number of voxels is very large in this case, right? So I think that's an important point. So keep that in mind. When we talk about microstructure, in this case, the number of voxels is 1000 by 500 by, let me go with 1 by 1 by 1 because it's easy to talk about it. So the number of voxels is, how much is it? 150,000, right? 150 million voxels. Right? Right? Does everyone get this? So the microstructure here requires I have to specify local state in 150 million voxels, and then I have microstructure definition. Right? Okay. So then the question is, how do I define a microstructure function? The intuitive way of defining this, if you just think of it very naturally, you'll say, oh, microstructure should be a function that maps location and time to the local state, right? So basically you're saying, as input, tell me what voxel you're interested in. For that voxel, because X tells me the voxel location, time, you give me those things, I'll tell you what is at that point. That's a very natural way of thinking of microstructure. Turns out it's not a good one, because it doesn't allow you to define things in a statistical way, because it's a very deterministic description. You're saying that voxel, I'm 100% sure that voxel is there. And if you keeping in mind where we are going, we have to deal with statistics. There is really no way around dealing with statistics. So we don't like that. Okay. Then there are also uncertainties, and basically what this is saying is that the reason you want this to be a statistical description is your machine is saying that the orientation is, let's say, 0, 0, 0, but there's only a certain confidence in that. You really are not 100% sure it's 0, 0, 0 orientation. Okay? And it always, the reason you have uncertainty is because there are machine limitations, right? There are always limitations in machines. And what this doesn't allow me to do is to talk about mixed states. So if I decide to do it this way, then every voxel has to be mapped to a pure local state. I cannot say that voxel has 30% of this state and 70% of another state. So this doesn't let me do that. Okay? So with all these reasons, we decide that we want to define it differently, and this is called the microstructure function. And here what we are saying is, we are going to define this as a probability function that says, okay, you specify the local state, you specify the voxel location, specify the time, and I'll tell you the probability of that happening. So m is the probability of finding that. So if it doesn't exist, the probability is 0. If it is completely there, it's 1. Okay? And the answer can be anything between 0 and 1. Okay? So this is a microstructure function. Now this is the definition of, because later we'll talk about density. So just pay attention to this word density. The reason the word density is there is because the variables are not discrete variables. So the way to think about density is that if you're thinking of a discrete outcome, then it's like tossing a coin and getting head or tails. Then you talk about probability, not probability density. But if the outcome is a continuous number, say, so you toss a coin and the answer is anywhere between 0 to 1, then the only thing you can talk about is a density, a probability density, right? Because there is no such thing as probability for a continuous number. Do you understand that? Okay. Okay. So we talk about continuous stuff. So the only logical thing to ask in this question, because particularly if you think of h as a continuous function, a continuous variable, so you cannot ask what is the probability of finding h at x. All you can say is what is the probability of finding h at x within a certain small window. That is a very valid question. And that then is a probability. But just m is probability density. Okay, that's the difference between the two. Okay. And it's important to recognize that what we are getting in experiments is really the probability, not the probability density. You get probabilities because in a machine, it actually averages it out, and within the machine limit, if you can measure, say, orientation within 1 degree, what you're getting is within 1 degree. So that's already implied in that definition. Right? So what you get from machines are probabilities. What you want to define are probability densities, to be more clear about what the function is. So having said all this, that's a definition of the microstructure function. I have no interest in using the continuous version because it's way too complicated. I want to use discrete version, so I'm going to discretize it. And the way to discretize this function is basically like this. It's an array. So one index goes with one variable, the other index goes with another variable. So you basically bin it. You cut it down into pieces, and you say it's a discrete representation. After you discretize it, these now become probabilities. This is now probability density. These are now probabilities, because you basically you take a volume, you cut it up into like this, right? So this is like voxelized. So now you're no longer saying what's happening at every point, you're saying what is the probability of finding a local state within that entire volume. So now it becomes probability. Okay? So this is basically a statement that says every voxel S, there are possibly n states, n local states, and this is the probability of finding a particular one in that particular voxel. But of course, if I add up all of them, all the local states, I should get one, right? Because it has to belong to one of the states. Okay? I'll show you how to, right now it's very discretized. I'll show you how we deal with things like crystal orientations, which are not discretized. So we have to do some extra work for that. So I'll show you how to do that, but we will discretize that as well. It just is a little bit more complicated. And each value of this, now in this definition, in the discretized definition, each value is between 0 and 1, because it's now back to probability. Okay? Again, if you already thought through this, then it's too much. What I'm telling you is too much, but otherwise, it is what it is. And an example of how to look at these numbers is, if I look at this micrograph and I think of every state as either white or gray. So the local states, H is only 1 or 2, right? So pretend that one of them is white, one of them is black. So if I look at cell 1, 2, so the cell location can be a vector. It doesn't have to be a single location. So when I write like this can be a vector. Okay? So I'm using vector indices. So for example, in 2D, it makes sense to identify each cell location by 2 integers. You don't have to, you can just do 1 integer, but you'll have to map it again. So this is much easier. And so if I look at this particular cell, what this says is, because I filled this cell with white, the probability of finding white in that cell is 1. The probability of finding gray in that cell is 0, basically. Okay? So this is a very simple way of making zeros and ones. You're reducing this to zeros and ones. So again, nothing complicated, I hope, right? And if you do that, this is the simplest way to do it. If you do that, you call them eigen microstructures, because essentially you reduce the image into zeros and ones, zeros or ones. So every element in that array is either a 0 or a 1 when you do this way. Okay? The theory doesn't restrict you to do that. The theory says you can put anything you want. You can put between 0 and 1, any number you like. But if you do this, then you call it an eigen microstructure. Okay? Now that's the easiest one. Now, then you can do, although it sounds very trivial, now you can basically build on that and do anything you want. And how we do anything we want is here. So let me see if I can go through this slowly. So when you bin it, that's a mathematical representation of binning, right? It looks very simple, but these are what are called as indicator functions. Essentially what it means is, if the position is inside the voxel, this gets 1. If the position is outside the voxel, it's 0, right? An indicator function is basically like a it's basically binning. It's called just binning, right? So if I take something like this and like this, so this is 1, right? That's this is an indicator function. These are called indicator functions. The chi's are called indicator function, and that's an indicator function. So let's say you're applying this on the spatial variables, x variables. So as long as x is inside that, that will get 1. And when x is outside that, this goes to 0. And of course, you need a lot of them. For every bin, you need one of them. And then you sum it up. So somewhere, every point is in some bin. So that's the one that shows up, and the rest go to 0. Okay, is everyone following that? The reason that is important is, essentially, these are orthogonal representations. The bins, the indicator functions, so one of them looks like this, another one might have a bin somewhere else, right? So I'll draw, I don't want to draw it there, but a bin is somewhere else. and those are orthogonal, right? If I multiply that and that, it goes to 0, right? The only time it goes to 1 is when I multiply the basis by itself, right? So if you're familiar with orthogonal representations, that's an orthogonal representation. And if you have more complicated things, all you have to do is to choose different bases. You don't want to use the same basis. This works well when you want to bin, but if you want to do something more sophisticated, you use other orthogonal bases. What could they be? There are many of them. This, for example, is using what are called as classical harmonics, right? You must have seen this. This is sine plus cosine, right? So this is a classical harmonic, and that's an orthogonal function, in fact, right? Orthogonal basis. So in this case, we are doing still binning on the local state, but we are using classical harmonics on the spatial variable. And the beauty is everything looks similar, right? I mean, so this is your discrete representation in case of binning. This is your discrete representation, except that now the microstructure is in a frequency space instead of the real space. That's the only difference. And still a discrete representation. This is still an array. Only difference is because of the Fourier representation, it goes to infinity. That's another problem, and we'll deal with that as we go along. But otherwise, it's exactly the same. Okay. The very in polycrystals, if anybody works with polycrystals, this is a very popular application. So we do a lot of work with this particular one, where now the local state is now orientation. Luckily, turns out there is a very nice basis for orientation. It's called spherical harmonics. So if you know what spherical harmonics are, these are spherical harmonics. So people have already worked out what that basis is. So we are just using, so we didn't invent spherical harmonics, we just use them. But it turns out this very, very efficient. It actually is amazing as to what it can do. So there is a little bit of learning to choose what is the right basis. Of course, I mean, for a simple microstructure like this, you don't have anything to choose. This is it. That's the end of the story. Okay, you go with it. But if you have something more complicated, for example, the one that I had, polycrystal, right? This one turns out, at least from our experience, turns out this is the best one. Okay, and again you can do, and so the most of the bases we use is either binning or classical harmonics, spherical harmonics, Legendre series. So Legendre series is another nice orthonormal basis. So if you have variables like concentration, where the value goes from 0 to 1, so these variables are always angles. So they go from 0 to 2 pi essentially, and there are symmetries. That's why you need all the symmetry stuff, right? Otherwise, these angles go from 0 to 2 pi. So they are basically sines and cosines, but very complicated sines and cosines. But if you look at variables like this that go from 0 to 1, for example, then Legendre polynomials, so they are polynomials, but Legendre polynomials are orthogonal. Normal polynomials are not. If you say x square, x cube, it's not orthogonal. These are orthogonal. That's the difference. Okay, and being orthogonal has a benefit. So it's actually very useful to have a orthogonal representation. So this is basically my microstructure representation. This is how mathematically I'm representing the microstructure. Right? And so let's see. Again, this just shows that you can do with any basis. You don't have to do binning or spherical harmonics. You can basically do it with any basis as long as it's orthogonal. And essentially, any microstructure with any basis, you still get Fourier coefficients. So there's nothing really deep I'm saying. I already said what I was going to say there. This is just an example of how that spherical harmonics works. And let's see. Yeah, so spherical harmonics are complicated. They look like that, but it doesn't matter. The main thing is that these are orthogonal to each other. So the entire basis is orthogonal. And once it's orthogonal, you get the value. And particularly the way it works out is just basically the value of the spherical harmonic for that particular cell. That's all it is. So it's once you understand how the Fourier series works, it's actually very straightforward. Okay, and you can add anything. So, for example, if I decide to have orientation and composition as my local state. I decide that they are both important. All I have to do is to find a basis for orientation, a basis for concentration, and then this is still my binning for the spatial variable, right? I still have x. For the x, I still do binning, and for everything else, I use Fourier basis. And essentially, it works the same way, and I still get a digital representation of the microstructure. This is now my digital representation. So every voxel has a bunch of numbers, essentially, right? And hope you can see the generality, and that's basically the microstructure part. Now, this is just microstructure, right? I haven't yet quantified it. Now I need to quantify it. All I have is numbers for each voxel. Okay? So now I have to quantify this. And we're going to quantify using spatial correlations. What does that mean? So spatial correlation, so when I'm going back to the simple case where every voxel is either white or black, and so my very basic representation, right? This is just full of zeros and ones, right? But of course, it's a different array for this microstructure, different one for this, different one for this, okay? But if I look at this, many of them look similar to each other, right? So the question really is, how do I quantify so that I can tell that some are similar, some are different? Are they different, right? Because at this point, if I just look at it as an array and I compare pixel to pixel, there's no chance they're going to match, right? Unless I have the exact same microstructure, they're not going to match, right? So I need something more than just this representation. This captures the image in an array, but now I need to look at some aspects of, some statistics of it. Okay? So if you start looking at the statistics, the obvious one, the simplest one, is what you call as the zeroth moment, or essentially what it is simply saying is, the way to think about, there are many ways of thinking about this, but one way to think about it is, I'm going to look at a particular cell in all the images. So I have multiple images. I'm going to look at, let's say, cell number 10, 20 or something like that, or 100, 100, right? I'm going to look at one of them. I'm going to ask, what is the value of that? And I have multiple images. So this one is all the images, right? This J is the number of images. If I take that particular cell number 1010, for example, in all the images, and just average it out, what will I get? Just the volume fraction, right? Basically. And that's what this is saying, right? It's a very roundabout way of saying it, but essentially what this is saying is, if I take a particular cell, average it out, I'm going to get volume fraction. Because it's volume fraction, it shouldn't matter which cell I took. If I do that on 1010 or I do it on 5050, you should get the same answer. So essentially you can say, well, this should be same as that, and this is a statistic. And this is what you call as 1 point statistic. Okay? This is volume fraction. So everything you do as volume fraction is nothing but 1 point statistic. Now you build on that. This of course is trivial, right? Everybody does this. Now you build on that, and now you ask, what would 2 point statistics look like, right? If that is 1 point statistic, now you say, what would a 2 point statistic look like? So in a 2 point statistic, what you say is, I'm going to take a cell as, I'm going to put a vector R. So the way we label them, for example, this vector would be 0, 2, because the x component is 0, y component is 2. This vector would be minus 1, 0, right? So if I take a particular cell, put a vector, now I'm asking, what is the chance that the tail has the state n and the head has the state p? What is that likely to have? What is the chance of getting that? So that's my statistic. Now, as I wrote this, it depends on S, but if I have enough data, there's no reason why that should depend on S, right? Because if I take the same vector and if I throw it in all the images in the same location, but if I have enough of them, whether I throw it in one location or I throw it in another location, it shouldn't make any difference. So this statistic again should be independent of S. There's no reason why that should depend on S. That's basically statistical homogeneity. That's the definition of statistical homogeneity. And now you can define a statistic where you are saying, if I randomly throw this vector R into the microstructure, so now I'm no longer throwing it at S, I'm throwing it anywhere in there. What is the possibility that the tail falls in the state N and the head falls in state P? That's the definition of a 2-point statistic. Okay. Mathematically, that's what it turns out. Because now remember, M is always a probability, right? To get the probability of getting N and P, I just have to ask what is the probability of finding N at the tail, multiply by the probability. It's a joint probability. What's the probability of this happening times what's that happening? So these are just mathematical definitions. So the M is exactly same as what we had before. So 2-point statistics essentially is nothing but a first moment of M, essentially. Yeah. But you do it for every R you can think of. So you're not doing it for a single R, you're doing for all of them. Okay? And that's where the trick is if you decide to do it this way, as it is written here, this is quite expensive. It's basically an n square calculation. So when we had 150 million voxels, if you do it this way, it would take 150 million square calculations. And that's where the trick is. It turns out you can do it much faster. Oh, I'm not getting there yet. So I'm getting ahead of the story. So I'll come back to that. So there's a way to do it very fast. We'll get to that later. So right now, just focus on definition. Don't worry about how we are going to compute it. Okay, and we'll get to computation. So one other detail is periodicity versus non-periodic. So you have to make a decision on whether an image like this is periodic or not periodic. Sometimes you want to make it periodic, sometimes you don't want to make it periodic. A lot of simulations, people who do simulations, they take microstructures and make it periodic. So then you want to use that because that's already went into your calculation, right? Sometimes you get a real image from a micrograph from an experiment, and then you don't know what is outside. You didn't take a picture, so you have no idea what is outside. So you should be able to do both. So the way to do both turns out is very simple, except that I just have to change the equation a little bit. So there's a small change. The numerator is exactly same as before. The denominator changes. And the way to interpret that is simply as the number of successes by number of trials. So in a periodic microstructure, I can throw the vector anywhere I want. I can throw it anywhere in the S. Because when I throw the vector and the head falls out, because it's periodic, if the head is here, I know exactly what is the state there, because I'm just repeating this, right? In a non-periodic, if I decide to throw this vector in a non-periodic, the only valid trials are as long as the tail is inside the gray box. So all I have to do non-periodic is basically adjust the number of trials. And that's a very simple calculation. Basically, it's literally this calculation. That's what it is. And then I can do non-periodic. Okay? So the numbers, now let's look at the total number of statistics I can think of. Because if I have two states, the number of possibilities I can define is 4, right? Because let's say I have white and black. So the number of possibilities is 4. If I have 10 states, I have 100 possibilities, right? Because every pair, right? I'm looking at every possible pair. Turns out of the 100, if I do this to 10 states, if I do this, then it turns out out of the 100 possibilities, only 9 are independent. The other 81 are dependent. So if you give me 9, I can compute the other 91. And that simply comes out of a relationship. If you are interested in the relationship, you'll find it there. But there is a way to compute them. So they basically so the number of independent states here is n minus 1, where n is the number of states. The number of independent correlations is n minus 1. So if I have 10 states, I only need 9 correlations. The rest are automatic. Okay? They're not linear, but they're automatic. I can compute them automatically. Okay? Okay, so this is actually the detail of how we do it. So turns out the way you compute is actually much cheaper if you do it by DFTs, discrete Fourier transforms, or FFT algorithm. The algorithm itself is called a fast Fourier transform algorithm. So I'm trying to see where. Actually, this is better. Let me show it to you here. So, this is the way you compute the 2-point statistics is you take the microstructure, you do a DFT on it, and then you do it for the 2 states n and p. You take conjugate of one of them, you multiply that. This is one frequency at a time. You are multiplying only this frequency with this frequency. There is no summation sign, right? You just multiply point by point, frequency by frequency, and then you do an inverse DFT, and then you get 2-point statistics. Again, this is a standard definition of convolution or a correlation. If you recognize that this equation is nothing but a correlation or a convolution, depends on which way you look at it. But this, I think, by definition, this is a correlation. Convolution looks a little bit different. I think there's a minus or something like that. It looks a little bit different, but mathematically they are very equal, it's very similar. Okay? So essentially, to compute this, it actually turns out if you do this in the DFT space, then this summation goes away. This is gone. And that's a bigger summation, right? Because you're doing it over every voxel. If you have 150 million, that's where it is, and that summation simply disappears. And it's the exact result. So this is not an approximate result, this is an exact result, and you'll get exactly the same answer if you do it by DFTs. So essentially what we do is take the microstructure, convert them to DFTs, do the operation, and do an inverse. And that's what, after you do the inverse, that's what it looks like. Okay. So in this particular case, the green is the actual micrograph, the green box. The outside one is just for you to see, basically extended by periodicity. So we took that extended by periodicity so that you can see what it looks like. But what was fed into the computer is what is only in the green box. Okay? And then you do autocorrelation and you see that. So the point here is you can see the symmetries, everything is preserved, right? So the features, all the features that you see here are here. In fact, the number of statistics is exactly same as the number of voxels here. I don't know if you paid attention to that. So if this is 10 by 10, then this is, I guess in this case it's 30 by 30. So this must be 30 by 30. And the number of voxels is exactly the same. The reason I'm saying that is we also spent quite a bit of time saying, if you give me this and don't show me this, I can reconstruct this voxel by voxel from here. So the point is there's a lot of information in this, and in fact we argue that there are a few cases where we are not able to reconstruct because the reconstruction is an inverse problem, right? I have the 2-point statistics, now I want to know what the original one looks like. There are a few cases where we couldn't do the reconstruction, but over 95% of the cases we can do an exact one-to-one reconstruction, right? So the main point is there's a lot of information here that it carries. It has volume. So the one that is obvious is the center, because the center is probability of finding this particular state at 0 vector. So that's nothing but in the eigen microstructures, when you have zeros and ones, the center is always volume fraction. So the 1-point statistic like volume fraction is always embedded in the 2-point statistics, and 2-point statistics are always embedded in 3-point statistics. They're always there, so you don't have to come back and do it again. Okay? But there's all the information. If you give me this particular one, where I'm pretty confident, you give me this, we can reconstruct that, no problem whatsoever. Okay? One to one, with pixel by pixel, you'll reconstruct that. Okay? So that's 2-point statistics. Okay? Anything I can answer? So now that's the one I showed you was the periodic case. If you do the non-periodic case, as I said, only thing I have to adjust is the denominator, and I have to do a little bit more work, but it's very simple work, no problem at all. Very simple stuff. The way to do that, still using DFTs, because in DFTs you automatically assume periodicity. So the way to do that is you pad it. So you basically, this is actual volume, you pad it with another state, completely different state, and then you do the same thing. Of course, this is much cheaper. Even if you pad it, even then it's much cheaper to do this. And when you recover the 2-point statistics, you can see because this is not periodic, I mean, you may or may not be able to see it, but you need to look at the numbers here and the numbers here. This number and that number are not the same because it's not periodic. The periodicity was not imposed in there. Okay. Now, you can do a lot of different games with this. Now you can say, extending the same idea, you can say, I have an image like this, but I'm not sure about what is inside here. Maybe I didn't get an image right. Maybe I didn't get it in focus. Maybe there is a scratch in there and I don't want to deal with the scratch. So the question is, can I have an irregular geometry? Let's say I only want to do 2-point statistics only in the white area. I don't want to do it in the black areas. Is it possible to do that? Turns out, yes, you can. Same idea. Instead of padding, now you mask it. And when you do it only in the white area, the 2-point statistics recover what you are expecting because you see the hexagonal symmetry, right? So the 2-point statistics still show you the hexagonal symmetry. Okay. So after I gave you the basic idea, I hope you can see this. Now you can basically do the same thing with everything, with anything you do. And the codes are all on PyMKS. You're welcome to download and use them if you like. And the same idea works with polycrystals. Now you just have to make sure you're using the spherical harmonics. Again, if you're following the equations, I know it's too much to follow the equations in a lecture like this because they're way complicated. If you're interested, you need to sit and go through them. And essentially, the 2-point statistics for the orientation looks very similar than what it looked for the black and white image. The equation looks very similar. So the same codes, essentially the same codes. After you just change the basis, everything else is exactly the same code. You're not doing anything different, and you get the same answers, right? So this is now a very generic technique. We can use it on basically, we argue, I mean, again, some of it is still not completely true, but we can now do this on anything. We have done this on atomic data sets. So you can give me an MD data set. We have done with phase field data sets. We have done this with finite element data sets. We have done this with real images. We have done this with basically anything you can think of. So far, anything that we got, we do the same thing. Okay. Okay. So the last part, before in the next 10 minutes, I'll finish this one, is dimensionality reduction. So I'm going to talk about principal component analysis. Does everyone know what it is, or how many of you know what PCA or POD? POD, PCA are the same, principal component analysis. Okay. So some of you raised your hands. For you, this would be trivial. For the rest, I'll just go through it very fast. Okay. So I have a high dimensional data, right? Again, at the end of all what I did in here, I still have a very large dimensional data. For example, this one, my statistics are 300 by 300, right? So this is still 90,000, right? 300 by 300 is 90,000. So one micrograph is 90,000, a vector of 90,000 elements, right? Still very high dimensional, right? But all I did is I got rid of all the rest of the stuff I don't care about, and I got a nice representation of the structure. All I got are the spatial correlations in the structure. That's it. I didn't do anything else so far. Now I'm saying that's too much. I don't want to deal with 90,000 representations of microstructures. And that was 2D. In 3D, it's another order of magnitude, right? Several orders of magnitude up. So I don't want to do that. So how do I get around that? So you basically look at very large dimensional data. So basically this is called, think of it as a data set or data matrix. The dimensionality is much larger than the number of samples. So, and this typically what happens in materials, right? We probably have dimensionality is in millions. Probably I'll have 10 micrographs, 20 micrographs. I'm not going to get millions of micrographs. There's no way anybody is going to do that. So the number of samples is much smaller than the dimensions. In this situation, you can almost convince yourself that there has to be a low dimensional representation, right? And in a pictorial way, all it says is this, something like this. So this is the data in the original dimensions. So these are the actual. So if I have 90,000 dimensions, this is a point in a 90,000 dimensional space. Right? I'm showing it in 2D, but basically think of it as 90,000 dimensions. Okay. But if you look at the dimensions, even in this picture, you will see that, especially when I have less number of points than the number of dimensions, there are always some new directions. If you express the data in a new frame, there is a much better way of expressing it. So it's this entire thing about PCA or POD is finding a new frame where you are compactly representing the same data set, essentially. Okay? So we only allow orthogonal distance preserving transformation. So the new frame has to be defined only by a rotation compared to the other frame. And we also do it by mean centering. So the new frame is always going to be at the mean center of all the data. So those are the two attributes of PCA. It is an orthogonal transformation, distance preserving orthogonal transformation, and it's mean centered. Once you do that, then you can say, for example, in this case, just as an idea, we're saying that direction 1 is good enough. It's capturing most of what I want to do. So I'm going to ignore 2, and I'm going to get to 1. This just shows you how you're going from 2 to 1, but I'm interested in going from millions to 3 or 5. Right? I don't want to get more than 10. Okay? But the same idea works. Okay? And that's called PCA. The math of it looks like this. This is an orthogonal transformation. You're mean centering, and you do orthogonal transformation, and you're saying, find me the direction that has the highest variance. And that is an eigenvalue problem. And the solution is basically an eigenvalue, eigenvectors of the covariance matrix. So this is the data. If you do transpose and transpose times this is what you call as a covariance matrix. The eigenvectors of the covariance matrix are basically your basis vectors, and the eigenvalues carry information on the variance. So the information on variance is completely in the eigenvalues. So it's a very nice representation. It's an orthogonal representation. It's very nice. And let me see if there's anything I want to tell you. Yeah, eigenvalues are still useful. Eigenvectors are the new directions now, and you basically transform. The transform quantities, we call them as PC scores or PC weights. Yeah, so these are new coordinates of the same point. Now you are seeing them in a new frame, and you simply call them PC scores or PC weights. Now, so when I store them, I store all of them. So if you give me the data, I'm transforming it. I have the new weights, but I still keep my mean and I keep the basis vector, because just in case I want to reconstruct, I want to go back to the old frame. I need those things, right? But I'm only storing them as one set of basis vectors and one set of mean. So the cost of storage is not that high. Okay? So we store them, and oftentimes, if you have 10 data points, basically you can say that because of mean centering, you can actually say that in the new frame, there can only be 9 coordinates. If you have 10 data points, you can only have 9 minus 1. I mean 10 minus 1. You can only have 9 coordinates. But oftentimes we are not even keeping 9. We are truncating way before that. And so we are truncating. So when you truncate, you are losing some information. But hopefully you lost only the information you don't care about. And the way you decide where to truncate depends on the eigenvalues, because eigenvalues tell you how much of the variance you're capturing. So you can look at the eigenvalues and decide where you're truncating. I'll show you some examples. So the way you do this is you actually don't find eigenvalues and eigenvectors. That's way too expensive. The simplest way to do PCA is through what is called an SVD decomposition. So any data matrix can be broken down this way. And essentially it turns out if you do it this way, you get the same answers, but you get them much faster. So the way most PCA analysis is done is through SVD, although the problem is formulated as an eigenvector problem or an eigen problem. So essentially, summary of everything I said. So all of that previous slides is math. Again, if you know what PCA is, great. If you don't know what PCA is, I encourage you to read it up. I think Wikipedia probably has a nice page on that. So read it up. It's used a lot in almost any field. So it's not something new by any means. But essentially what it is I am looking at the 2-point statistics. We are mean centering. We remove the mean. So now I have hundreds of images. For each image, I have a vector. I have 2-point statistics. We mean center it. The rest of it, after you take the mean out, the rest of it can be cast into this new frame. And so these are your new directions. These are the new weights, essentially. And this is what we are using to represent the material. So we are saying this carries all the information I need about the microstructure, essentially. Because that's what it is, right? If you give me these if you give me the PC weights, I'm using the basis, I can reconstruct this. Of course, this is approximate because I truncated it, right? Otherwise, it's actually more or less exact. If I keep all of them, then it's exact. So the way that works essentially is, so imagine just doing this as an example where you're doing 900 of this. There are 5 classes. So you're doing multiple ones. And then you take the image, convert to 2-point statistics. You get 900 sets of 2-point statistics. Then do PCA. And now if you look at each micrograph in the PC space, so what you're seeing are 3 projections. I'm looking at in 3 PCs, PC1, PC2, PC3, but I'm showing you 1 projection at a time. And 1 micrograph is one point, right? Every point now is 1 micrograph. And what I'm showing you here is that different patterns. There are 5 different ways the microstructure was generated. So there are 180 of these, 180 of these, but not all 180 look like that. They are similar features, but they don't look exactly like that, because each class, the volume fractions were changed, right? So they don't look like that, exactly like that way. But even in 3 dimensions, the 5 classes can be separated. You may not be able to separate them in one of them, but if you look at all projections, you'll see that every class looks different. So there is separation even in just 3 principal components. Okay, the size, then the pixel size of this, if I remember, was 81 by 81. So this 6,000 something, 6,400 dimensional representation. So the full representation of each microstructure is 6,400 dimensional. I'm reducing it to 3, and I'm arguing that I have most of the information I need to build a PSP linkage on this. Okay. Again, I'll show you more details as we go along. What does it really mean? I now have the mean and I have the PC basis. So you give me a new microstructure, I subtract the mean, whatever is left over, I'm going to project it into the 3 bases, and I have PC scores. Okay? And so I have 3 numbers. So for example, this is actual autocorrelation. These are the 3 numbers. Because I truncated it, if I construct it back, I have to take the mean, I have to add the first basis, the second, third. So this is my approximation to the real one. This is the real microstructure, 2-point statistics. With 3 of them, I get this approximation. And again, the argument is that they're close enough. And if I build a process structure linkage or a structure property linkage, where the structure is represented by 3 numbers, I get very good models, essentially. Okay? So that's basically the storyline. Now, there are other dimensionality reduction techniques. You don't have to do this. There are many other ones. But this is nice because it is orthogonal. There are, again, if you're interested, I can show you other ones. For example, there's a kernel PCA. So there is another one called kernel PCA. Seems to work reasonable, but so far we haven't found any reason to go beyond this. This works very fast and very simple, and we get great models. I'll show you some examples in the second half. But essentially, hopefully, at this point, you understand what we mean by microstructure representation, right? So we basically, if nothing else, there's an image. Then we do spatial correlations, 2-point statistics. We say you can do n-point, but we mostly do 2-point. We can do n-point, but we find that there's no need. Most of the times, we don't need anything. So we do 2-point. Sometimes we do a little bit more. And then we do principal component analysis on the spatial correlations. By the way, a lot of people have tried to do PCA directly on the images. There, most people report they need something like 50 to 100 dimensions in the low dimensional representation. Most of what I'll show you, we need only about 5 or 6, and we can build incredibly good models with this technique. Okay, so this is much more effective than anything out there in that sense. So that's what I want you to remember: the image, spatial correlations, low dimensional representation. And basically, once you have low dimensional representation, most of the game is done, right? At this point, you're just using that to build a model. And at this point, there's a whole lot of machine learning tricks out there, machine learning algorithms that can do the job. Okay. Okay. So let's go a little bit further, and then we'll see whether it makes sense or not. Any other questions? Okay. So now that we got this, we want to build these models, right? So we'll see what kind of examples I have. But yeah, I can show you a lot of different background stuff, a lot of different papers. If you're interested, I can send it to you. So we have, at this point, we probably have about 50 case studies out there in papers and books and things like that, that demonstrate basically the same thing works in almost all case studies. So now we are pretty confident about what we are doing. Okay, in terms of the theories, composite theories, particularly going from structure to property. The composite theories are most developed on this side. On going from process to structure, the composite theories, the analytical versions are not that well developed. So it's kind of complicated to go that side. Okay. On this side, things are much better developed. People have been working on this for 100 years or so. And essentially, a typical problem looks like that, right? So this is just a notation convention. The governing equation, the field equation, is nothing but equilibrium. Right? Does everyone recognize this notation? People understand this? Any questions on the notation stuff I can explain? No? Everything looks good? So basic Einstein notation: repeated index gets summation, comma is derivative, stress is stress, right? Everybody knows what stress is, and body forces, right? So that's a standard equilibrium equation, right? Okay, the composite theory problem is formulated this way. Basically, you're saying that there is a constitutive equation at every point in this volume, at every point x, stress and strain. So this is written for elasticity. For plasticity, it's very similar. Right away, you might say, well, it's linear and not linear. It turns out, again, a lot of smart people have worked on this for about 100 years. So they are able to make the nonlinear one look like the linear one. And there's a trick to doing that. But they're incredibly smart, and they do it. Okay. Again, none of that comes from our side. Even all of this comes from previous work from other people. In fact, one of the guys who did this is actually from Germany. His name is Kroner. So if you want to follow some of this, you need to follow Kroner's work in 60s. This is when they figured out all this stuff in 60s, early 60s. Okay. Okay. So this is the constitutive equation. This is the stiffness tensor. We know it has to be for elastic stuff. I'm only showing elastic because it's easy to go through. The rest of them, the derivation is exactly the same, but the terms are a lot more terms. So I don't want to go through that. So the stiffness has to be positive semi-definite. This is the equilibrium equation, the same equation I wrote last time, but essentially the body force is gone because there are no body forces here. So that's, and this is a continuity statement. So nothing complicated there. Right? This is a very standard mechanics statement of a composite problem. Now, homogenization theory says if I have this description of the problem statement, it actually says that this relationship is exact. Okay, so it's not obvious, right? You cannot just look at it and say, because this is true at every point and all this has to happen, this has to happen, right? But somebody has proven it, and actually I think the proof is by Hill. I think there's a paper and a book by Hill, and he shows you how that proof is. It also uses what I said in the morning: separation of scales and statistical homogeneity is a part of the assumption. That's why I say that almost every composite theory assumes separation of scales. Otherwise, there is no solution to this problem. Okay. So once you make those, then you can prove. So this is not an approximation. This is not a hypothesis. This is for elasticity. It's a rigorous proof that this exists. where sigma bar is simply the volume average and epsilon bar is simply the volume average. That's the definition. And effective stiffness, which is the homogenized property, because if this exists, basically what you're saying is when I go to the higher length scale, I can assign this and I should have basically the same response at the higher length scale. Okay? The problem is the effective value is simply not a volume average of this. If it was, life would have been simple. You didn't have to worry about anything, and life, nobody would, do any mechanics anymore, right? So turns out it's not just a volume average. Now, I don't want to go through all of this, but I'll go through the main idea, right? Because the idea is very important, and it's amazing that people did this 60 years back, or 1950s is when they figured this out. And the idea is the following. It's actually a very cool idea. What you're saying is, if I take this strain and write it as an average and a perturbation, right? I can always do that, right? You can take the strain field in the RVE. I can always write it as an average and a perturbation. Then I can convince myself that the perturbation at every point x depends on the macro imposed strain. This is a macro. Anytime you see a bar at the top, it's a volume average quantity, right? So if I impose a certain strain, average strain at the higher length scale, the local value, perturbation in the local value can be related through a fourth rank tensor, and this is called a localization tensor. So you have to first prove that this exists, and then it does, and they have gone through the proof. They have shown that it exists, and once that exists, then you can say the effective stress. We know, we already said that this came from the last slide, right? This is what I started as a homogenization theory thing. But of course, the average stress is nothing but the average of the stresses. So this is to the, and if I equate these two and use that idea, then it turns out the C effective is nothing but C bar plus C times A, this one. So the nice thing about this is you can see it no longer depends on what you impose as strain, right? So now I have an equation for C effective simply as a function of the C at each location and this localization tensor. So the effective value can be rigorously solved if I know how to get the localization tensor. That's the only problem standing in our way, right? Does everyone see that? And the localization tensor, the rest of the story is localization tensor, will depend on the microstructure, right? So the microstructure information is going into the localization tensor. Okay? So the way they solve it is, this is the cool part. So this part is very easy to, up to here is very easy to prove. The cool part is to show that, so the same perturbation, you also do it on C. This time you use a reference value. So you have to pick a reference value. It can be anything you want, and then you do a perturbation on that. And if you do that, this equation reduces to this, but that's not that important, right? The important part is here. So if you put the C and then you go back to your equilibrium equation, remember this equilibrium equation, right? This is equal to 0 is the equilibrium equation. That has, in elasticity, has C. This entire thing is C, right? This is same as this, and this is the total strain. So each one has been broken up. In this case, a reference value and a perturbation. In this case, an average value and a perturbation. You could always use the reference. You can also say, I want to use a C bar here. Then you made a choice that the reference is same as average. That's your choice. But the theory works anyway. Okay? So you break it up. Now you expand it. There are 4 terms. Out of the 4 terms, one product is when you take a derivative, because this is a constant. That's a constant. So the derivative goes to 0. So there are only 3 terms remaining. So if you expand that out, you get 3 terms. Then when you look at this, and this is the cool part, what they say is, if I want to solve this, this is complicated, right? Because this is a constant, right? Notice that this is a constant. And this is what I'm trying to solve. Because, right, I mean, remember, if I know epsilon bar, I can back out A. This is what I'm trying to solve. Now, there are lots of complexities in these 2 terms, right? But now if I think of it as a Green's function, so this is called a Green's function solution. What they're saying is the solution to this equation is much more efficiently done if I think of this problem as this problem, right? Remember, all I did is collected these two terms and I called it Fi. That's it, right? Nothing tragic or nothing complicated there. Instead of solving this problem, I'm going to think of it. So I'm basically thinking of these two terms as a fictitious body force. So in real problem, there is no body force. There is no body force in my real problem, right? But since the form of it fits that, I'm going to think of this as a fictitious body force. And if it is a fictitious body force, all I have to do is to solve this, because this is a constant. Remember that, right? This is a constant. So this has a Green's function solution. So basically, I have to solve it for a unit body force at a particular location, and then just convolve with the real body force, and I get the total. I get the same answer, exactly the same answer, not an approximation of any kind, nothing. It's exactly the same answer, right? So this approach is called a Green's function approach, and essentially what you're doing is you're solving this equation for a delta function. So delta function is a unit load in a particular location. So instead of solving this problem, I'm going to change the body force to a unit load. I'm going to solve this problem. The solution, I'm going to call it as G. Whatever u I get, I'm going to call it as G, because Green's functions are solutions to unit loads, right? You put an unit load and you solve that. So instead of solving this problem, I'm going to solve this problem where my unknown is this. This is my unknown, right? Everything else is known, right? Do you see that? Everything else is known. This is my displacement. I'm going to solve that. When I solve that, the solution is what I call a Green's function. Okay? Once I get this function, I have no interest in this particular problem, right? I have to go back to this problem. And this problem is nothing but Green's function convolved with the actual body force. And then I get the real solution. Go ahead.
C0 or CR, usually mean field approach or self-consistent, you have to choose in a certain way or converges towards the wrong answer, doesn't converge at all. It's not the case here?
No. So I'll get to that in a minute, because it's a series solution. So we are not. So there are iterative ways of solving, and there is a series solution. There are a couple of different ways of solving. So I'll try to point out what self-consistent people do. That's a totally, but we are not doing the self-consistent. So just to give you, let me back off a little bit and give you a little bit of a view of this. Is in the self-consistent approach, people assume an elliptical inclusion in an infinite medium. So I don't want to do that. Here I want to be able to put any microstructure. So I don't want to put any restrictions on what the microstructure looks like. Okay? So I'm not going the self-consistent direction. But they do start this way. They also talk about the same Green's functions. So up to here, we do exactly what self-consistent people do. They will change it in the next slide. Okay. Right? Does everyone follow this? Again, this is not a new idea, has been around since 1950s or 60s, 1950s. And so I know some of you are using the Fft method. This is where you start. This is basically the Fft method. We just change in the next slide, right? This is exactly what happens in the Fft method. Okay. Any questions on this? Okay. Let's move on. So you add that. You get the solution. So this is the Green's function solution. You do a little bit of manipulation because you like to get these derivatives on the right term, essentially. But basically, you do a little bit of manipulation here. And what would be useful for you is to keep this in mind. I get u. I want to convert this equation to look like this so that I can get A, right? My interest is in finding A. If I find A, I solve the entire problem. I don't need anything else, right? So I start with this, and I want to get a result that looks like that so that I can get an A out. Okay? So it turns out it's not that simple, because that's why it's a clever idea. It takes a while to do this. It's a very clever idea, which is if you do that and you do manipulations, you'll realize that there is a epsilon bar here, and then there is an epsilon prime here again. So epsilon prime is on this side, and epsilon prime is on this side. But you can take them out and kill the epsilon bar, and essentially you're left with A, but you get an A here, right? Okay. And up to this point, pretty much everybody is the same, self-consistent FFT methods, everybody is same. From here, they change to different directions, right? So in the FFT method, basically you start here and you iterate on A until you get the right A. Basically, you're iterating on it and you're solving it. That's one way of doing this. And all the FFT methods, Suke and Lebenson and all that, that's what they do. Basically, this. Go ahead.
Sorry. So for FFT, they just, if you consider finite strains, they use F and P and the non-symmetric part of the gamma operator, but the full version. If you just change F, the epsilon to F and your sigma to P, and you change your symmetric gamma to the full gamma, does it also work in your case for finite strains then?
So this is not, I mean, obviously this is elasticity, this is not finite strains. So you have to start with the constitutive model for plasticity to see how it works, right? So we haven't done that part. We haven't done the, you'll see that we are going a different direction. I think the FFT method with the finite strains, still there are issues. I don't think it's that clean as far as, you know, I know. I mean, again, I might be the wrong person to talk about that. But I think it's not that. I think there are still some challenges there. But nevertheless, if you stick with this problem, the Suke, original Suke work, essentially you solve for A in an iterative way. And it gives you fantastic answers. It's actually pretty good. It gives you fantastic answers. That's one way to do it. Another way to do this is to substitute this back in this. Right? So it's a recursive equation. You take this entire expression and put it here. Then you'll get another term, and then you'll get another A. And then put it back again. And then you get one more. So you'll basically get an infinite series. Okay? And this is Kroner's approach, Kroner's work. And again, the idea was there even before mechanics, but Kroner did it in mechanics for the first time. And essentially what you end up with is a series. And then from that series, you can actually prove that the effective, because remember A, once I have A, I have C, right? Remember this. Once I have A, I have C. So if I put it back, it's a series. So A is now a series. If I put it back, I get this expression. So the reason we like this, at least the people in our way of thinking, we like this because I'm going to show you that this term depends only on the 1-point statistics. This term depends only on the 2-point statistics, only, right? And this term depends on 3-point statistics and so on. So what this theory says is the right information about the microstructure that goes into the composite theory is actually endpoint statistics, nothing else. There's nothing else that comes into the composite theory in this form of expression. Is this the only way to do it? No, there are many other manipulations you can do. But this is the cleanest one and the easiest one that connects to endpoint statistics. Okay? So just to show you how it connects to endpoint statistics, if you look at a term like this, what it really means is C prime at x, C prime at x prime, and then this is T is nothing but x minus x prime. So a term like this simply means that. That's what that's the condensed notation. This is a condensed notation for a term like that. And if you look at it, essentially you're saying if I take 2 points, x and x prime, how many times am I going to find h at x, h prime at x prime? If I know that, then I can evaluate this integral simply by using the number of times I reach that. And essentially these two are completely equivalent. Right? And so you'll have to think about this a little bit because, right, I mean, if you give me a function and you're asking me how do I do, right, I mean, how do I integrate, right? This is basically any integral is an integral. So if you give me a function and you want to integrate, one way is to integrate this way, right? You take all the small things and add it up. That's the first equation. Another way to integrate is to look this way and say how many times am I getting a particular value, and you can integrate. Either way you integrate is the same answer. Yes, that's the difference between the two ways, and I think They have names for it. I think one is called Lebesgue integral, the other is called a Riemann integral, essentially, but they are completely equivalent. Okay, so so what this suggests is that this term depends only on the 2-point statistics. They are coefficients, but they are all linear coefficients. They are constants, and therefore I should be able to write this expression. So in terms of my principal components, remember my 2 points. Principal components are linear transformations of 2-point statistics. Remember that, right? I did that on purpose. I only did in PCA is just a linear transformation. Because it's a linear transformation, this automatically means this term can be written in terms of the principal components just as a linear equation. There is nothing else there. It has to be a linear equation. Okay? So every term in my expansion is linear in terms of my PC terms, basically, for elasticity. For other things it may not be, but for elasticity it is. So typically what it means is that in homogenization, I should get a linear expression in my principal components. Now the other part of it is my series expansion. How good is my series expansion? Maybe I'm not very good at that, right? So what we do is we allow polynomial combinations of this, because higher order statistics, so if I don't have any better idea, if I am looking at 5th order statistics, I can approximate it as products of 2nd order statistics and 3rd order statistics. Right? They are not exactly equal, but it's a good approximation. So if I do that, that translates to just polynomial terms. So the difference between here and here is, if my PC scores are alpha 1, alpha 2, here I'm looking for a linear expression in alpha 1, alpha 2. Here I'm allowing products of alpha 1, alpha 2. So I'm allowing alpha 1 square, alpha 2 square, alpha 1, alpha 2. I'm allowing products of them. And that's my model. So I'm going to build a model, the structure property model, using this. So this is my property. These are my principal components. Okay. So how do I know when I build a model, how good is it? I'm going to look at errors. So these are straightforward error definitions. So if this is a real value, this is my model. I'm building a model. This is my model. I'm going to take the difference, absolute, divide by some sort of a constant, and express the error as a percentage. Okay. So then I'm also looking at the average error. I'm also going to look at the standard deviation in error. So I'm not just looking at only the average, but I'm also looking at standard deviation. One other thing we do is, whenever you build model, you always have to do cross validation. So think of leave 1 out. It doesn't have to be leave 1 out. You can do leave 10 out, leave 100 out, whatever you want to do. There is a way to do it. But it's easy to think of leave 1 out. So in leave 1 out, what you do is, if you have 10 data points, you build the model on 9, leave 1 out. So you build the model on 9 and find the error for the 10th one. And then you repeat the model again. You do it on all combinations. Basically, you leave another one out next time, and then you leave another one out next time. And so you do it again and again. And then you get an error measure, and again you do the same thing. You get an error bar, and you do a cross validation error, and you do standard deviation of the cross validation error. Okay. So the advantage of doing these things is, now you can start deciding which model is good and which model is bad. Typically what happens is, as you increase the number of terms when you build a model, the error always goes down, right? If I have 5 points and I allow 5 parameters in the model, usually I can get 0 error, right? Generally speaking, right? Because I can make it go through all 5 points, right? But the cross validation is going to be lousy in that situation. So typically what happens is, cross validation tells you something about how overfit, how sensitive it is to the data. And if it is an overfit, it tells you you're basically overfitting. Okay. So just as an example, I'll show you an example. So go back to that example. This example came out of metals industry. Somebody was interested in particles precipitates in a matrix. They're looking at localization and things like that. So they're doing all of the data is generated by finite element simulations. So these are the microstructures. I already talked about this, right? So I'm not going to go back to that. But now every simulation, every one of the microstructures was simulated with finite elements, and they basically decided these are the things, these are the properties. So yield strength, that's obvious, right? Effective strain hardening. Strain hardening is important in these things because higher the strain hardening, you get better ductility and things like that. One of the things these guys were interested in is in localization. So they wanted to understand localization, and this one they simply defined as the area fraction of the matrix elements experiencing a strain greater than a certain cutoff strain. So if the strain was higher than that, they counted that as something bad, and they're looking at the number of elements, matrix elements that go through that bad strain, and that's what they call as localization. So we're building models for 3 properties, right? So property here, this is property 1, property 2, property 3, and we have 900. So we have 900 simulations like this. So we have 900 data points basically. Each simulation produces 1 data point. Okay. Now when you build the model, you're getting errors, and then this is cross validation error. So this is basically using all the data points. This is some sort of a cross validation, leaving some out and then doing it again and again and again. The difference between these two is, so what you are seeing here is a higher polynomial degree and the more number of PC scores. So if I use, as I increase the number of PC scores, as I increase the degree of polynomial, I get better answer all the time. I'll consistently get better answer. But what you're also seeing in the cross validation is, as I put more and more terms, at some point the error actually increases. So what it's telling you is it's an overfit. It's too sensitive to the data points. So you look at both of these and you can basically decide. Usually you try to minimize the number of terms. So it looks like you probably get something here. This looks like a good model because you're not really gaining much by going from here to here, right? So this is probably from this picture we would probably pick this one, right? Does that make sense? So that's how we pick models, and again the models look like that. So these are the terms, these are the polynomial terms. So the models look like this. The localization obviously has many more terms in the model. The yield strength doesn't have that many constants, only 3 terms, and that's it. That's all you need. So the models are relatively simple and they work pretty well. So there are a lot of examples of this, right? So I don't want to, but I hope you're getting an idea of what we are doing. So I just want to go through the couple of different models and then we can talk about plasticity. I'm hoping plasticity is what you're interested in. So that was homogenization, going like this. Now I want to talk about localization, which is now the harder part, remember that. But it's based on the same composite theory. So the theory is exactly the same. So I want to be able to do this problem now. So now I want to be able to put, suppose elasticity, I want to impose a macro scale strain, and I want to know the strain at every point in this voxel, in the model. I want to predict each one, every one of them. Homogenization, I'm only predicting average values, right? So it's the same equation, then there's no difference, it's the same equation, it's a series, and people have tried this. So people have done solutions to this in some case. But now I'm going to do it in the notation that I've shown you. So in the notation I've shown you, that equation looks like this. So when you look at an equation like this, you're saying this is now my strain in each voxel, right? This is my local strain in each voxel. That depends on this kernel depends on the Green's functions. So that gamma is essentially related to Green's function. So these are my Green's function related kernels. This is the same microstructure that I've been using before. So this equation is exactly equivalent to what Kroner derived for the composite theory. So this equation and the next one are exactly the same. Okay. Now, in the way people were doing it before, they were trying to analytically solve this and see whether or not this entire thing converges. The way we are doing it is the opposite way, is we take data, we run the simulation. So every time you give me one simulation, I know the microstructure and I know the output, right? Because I'm doing a finite element simulation. I'm using the finite element model to generate data. Right? So, if I have 100 microstructures, each microstructure in each voxel, every voxel gives me one data point. Right? So, it's easy to generate a lot of data points. Then from the finite element results, I'm calibrating alpha. And once I calibrate alpha, then I'm saying, okay, you give me now a new microstructure. You can give me anything you want, because if I believe the Green's functions are completely independent of microstructure. Again, if you're not sure, you have to go back and look at these in detail. There's nothing here that depends on M. This is completely independent of microstructure. So, Green's functions are completely independent of microstructure. So, if I can get good ones, then you can give me any microstructure you want, and I'm going to predict the answer. That's the hypothesis. Okay? And I'll show you that it works really well. Now, the one problem in this is, how am I going to calibrate this? It's regression, but turns out there are some tricks in there. So, again, DFTs help out, because otherwise the number of summation, you have to pay attention to the summation signs, because this term, the number of T is same as the number of cells. So, if I have 100 by 100 by 100, then this is a million long. So, this is fully coupled. So, if I want to do a regression in this space, then I'm building a, basically the number of unknowns is million. So, regressing over a million variables is very complicated. Whereas, if you do FFT, then that summation sign on the T goes away because of the convolution, it completely goes away. So, in the frequency space, the summation is only on the number of states. So, if I have only 2 states, this has only 2 unknowns, just that I have to do all the frequencies. So, in one way, I have millions that are coupled. Here, I only have only 2 or 3 things that are coupled. The number of unknowns is exactly the same. It's just that I'm solving 2 at a time or 3 at a time. Okay. So, the math is, unless you are familiar with all this, it's a little hard to go through. I would encourage you to look at it if you are interested in that. But now I'm going to show you proof that it works. Right. So, the examples I'm going to show you, I'm going to use this as my calibration. So, if I have a 2-phase material, I have a black phase surrounded by white, that's one material, one data point. Then I have white in the center surrounded by black. So, I use only 2 microstructures, and then we run finite element simulations on this. I get my Green's functions, or the kernels, Green's function based kernels. Once I have the kernel, I'm saying you make up anything you want. For example, this is you make up anything you want, and then I'll predict it for this. Right? And the reason I'm saying that is that this is not an interpolation of this. Right? Now I'm able to extrapolate, and I cannot do that until I have some physics in there. Right? And this is the proof that it works. This is 2-phase materials with, so this is actual microstructure. It's the contrast is 50%. So, one of them is 50% stiffer than the other, and this is a midsection of both. This is what we get from the method I showed you. This is what you get from the finite element method, and you can see that it's almost identical. You can hardly tell the difference. Right? If you look closely, you'll see some differences, but it's very hard to tell the difference. And this is elasticity, and you might say, well, elasticity is easy. Turns out you can do that with plasticity. So, now we have 2-phase material again. This time it's not those blocky stuff. These are now, they look more like grains. That's why the fields look like this. And this time the dimensions are 91 by 91 by 91. So, the number of pixels is almost a million, right? 100, almost 100 by 100 by 100, but it's actually 91 by 91 by 91. And again, midsections. So, the actual simulations are 3D. I'm showing you midsections, and these are particular strain rate. So, in plasticity, we impose a global strain rate, and we want to know the local strain rates, each component by component, and this is one of the components. And of course, the MKS part is very fast, incredibly fast. You can do it with very little resources, right? Because of the DFTs. All I'm using are DFTs. I just need to do one DFT because the kernel is already in DFT. I have to do 2 because I have to do an inverse DFT. So, I have to do 2 DFTs, and then it's over. Another advantage of this is because of the kernels, I don't have to, when you change the size, I don't have to redo the kernels. The kernel, once I do it once, I'm done. So I am doing this on a smaller volume, get the kernels, and then you can give me something that's much larger, right? And I can still do it pretty fast because I'm basically using the same Green's function kernels, right? Now, so far I only talked about the first term in the series. I don't know if you're paying attention to that, but there are other terms. So far all the examples I showed you had only this term. And now the question is, what is in there? It turns out higher the contrast between the two, the higher order terms make difference. So examples I showed you, the elastic one, this was only 50% stiffer than that. In plasticity, this was only twice as hard as that. So the ratio, the contrast was only 1.5 and 2 in the two examples I showed you. If I increase the contrast, it turns out the higher order terms become important. Now, it looks like it's a lot of terms, but it turns out this is just saying that as the contrast goes up, so that when the contrast is low, the predictions are in very good shape. As the contrast goes up, they are not very good, right? As the contrast goes up, it turns out the higher order terms are simply telling you more information about the neighborhood. So before, in the first term, when you pick a value for this, it really doesn't know what the neighbors are in this term. But in this term, it knows what the neighbors are, right? So it's actually systematically going through the neighbors. So essentially, this term, if we account for the neighborhood information, suppose you look at the one in the center and you look at the 6 neighbors, and each one you say can either be white or black, the number of configurations is 2 to the 7 because there are 7 spots, center plus 6 neighbors, and each one can be white or black. So there are 128 configurations here. So if you think of configurations, this term looks like that, and this term is exactly same as that. So you're back to the same protocol. You just have to learn how to compute them and think in this direction. So if you do that, essentially you see that answers are much better. So this is just the first term. So you can see they're not doing that well. But by the time you add the neighbors, the more neighbors you add, the better it is. And by the time you add neighbors, you're pretty close. This and this are pretty close, right? So you're getting higher order terms. So it proves that the theory actually, because the theory was already proven. I mean, anyway, we are not proving it. We're just saying that we are using it right. All this proves is that we are using the theory right? And what is impressive is that it's not just the distribution, but even the tails get better. So you can actually get tails, and this is important because if you're trying to predict fatigue-like properties, then the tails become very important, right? So let's see. This basically says that for polycrystals, and I think this is where you are asking, how do I know spherical harmonics work out better? This is, for now I'm doing this on polycrystals. Every other example so far was black and white. Now I'm doing this on polycrystals. Except that now I'm going to express the kernels in a Fourier series, the microstructure in a Fourier series. This one I already showed you before. Not only the microstructure, but the kernel itself I'm going to express in a Fourier series. So if I do this, the term here looks very similar to what I had for the black and white, except that now the terms are in the spherical harmonics. The advantage of this is that this coefficient, so this one can be anything it wants, but this coefficient for elasticity, you can actually theoretically prove that for example, for cubic metals, only L equal to 10 are non-zero. Everything above that has to be 0. So there are some of those theorems that actually work out, and it turns out, so I can represent this in a very compact way. In fact, there is no other compact representation for this term other than with spherical harmonics. Spherical harmonics give you the most compact representation of this term. And you can actually theoretically prove. For elasticity, you can theoretically prove it. For other ones, you cannot. I mean, at least we haven't figured out how to do it, but others might have. So that's the answer to why we do spherical harmonics. Is the number of terms here is the minimum you can get in this particular case. In the elastic case, it's the minimum. And it works because now you can give me, the advantage now is once I set up the kernels, once I have the kernels, you can make any microstructure with any cubic anisotropy ratio. These are different anisotropy ratios. You can make any polycrystal any way you like. We are not going back and creating the kernels again and again. It's just one set of kernels, and that's it. Now you make any one of them, we'll give you the answers just like that, very fast, right? And again, same thing. The speed is much lower. You can make up any polycrystal with any cubic constants that you can think of, and the answers are very fast. Okay. So, one last example of how we are putting it all together into plasticity. So, in plasticity, we are generally interested in multiscale. So, this is how we started. I mean, the entire reason for all of this was doing multiscale plasticity. That's how this entire thing started. So, some of you may know that we do a lot of work in plasticity, and this is where it started. So, what we really want to do is a simulation like this. This is ECAP. Some of you might know what this is. And if I do macro scale plasticity, then I'm not paying attention to details of microstructure. I have to assume something about like a Hill criteria or something, and then I have to do anisotropy, but it's I cannot pay attention to microstructure. What we really want to do is to be able to embed an RVE at every point and then basically run it through. At every integration point, you want to keep an RVE in there. Right now, doing that is impossible. There is really no computer anywhere that can do that with the number of, because this is pretty heavy plastic deformation. So, the number of elements you need is pretty high, and then now you have to put another RVE inside that. That's almost impossible. So, the strategy that we are going to do, again, this is the knowledge based thing. So, I'm trying to show you that all of this is very practical and is going to happen. We are almost there. The strategy is the following, right? So, there are two approaches. We either go this way or that way. This side is the cheaper way, and because it's cheaper, it's also not as accurate. That side is the full-blown, what you call as a full field approach, and what you call as a mean field approach. So, this is a mean field approach, that's a full field approach. In the mean field approach, what you do is, yes, you still imagine that there's a volume at every point, but you're using this volume mainly to what you call as partitioning. So, you're imposing a strain rate here, and you're breaking it down to what is the strain rate in this phase and what is the strain rate in that phase. It's still mean field, so it's phase averaged partitioning of the imposed strain rate. Right? So, I'm going to use a database for that. I'm going to run many of these simulations one time. I create a database. After I create the database, I'll never run a simulation at this scale again, ever. Okay? You make up any microstructure, you impose any strain rate, I'll tell you how much it's breaking down into the two phases, just like that, instantly. Okay? Once I do that, in the mean field approach, we are using a Taylor model. So, we are going to run Taylor code, because now each one of these has polycrystals. Each one has polycrystals and grains. So, we are going to use the Taylor model. Taylor model is also expensive. Running the Taylor model is also expensive, because we want to be as fast as a normal plasticity run. So, we want it to be, this entire thing to be just like that. Okay? So, this is going to slow you down. So, we create another database where basically you can put any strain that you are imposing on the polycrystal, grain by grain, it will just do the calculation and it will do it incredibly fast. So, by not doing the calculation, but we do everything beforehand, we create a database, and that's our database too. So, on this side, I need two databases, and I can predict anything you want. But of course, that's mean field approach. On this side, I'm saying no, now I don't want to do that. I actually want impose a particular strain here, strain rate here. Plasticity, you think in terms of strain rate, not in terms of strain. You impose an L, velocity gradient tensor. You compute the local L, every component of local L for every voxel. Okay? And that's the localization. And once I have that, I have to think of an update of the microstructure. Because of the plastic strains are large, the shape is not the same. So, if I start with something like this, it distorts to something like that. It's periodic, but it distorts to this. But for me to be able to apply this, I need to put this back into a nice square, right? Because remember, I'm using DFTs. So I cannot apply DFTs on this because now the points have moved around. So I have to remap it back to a microstructure, right? So I need one database for doing this. This is really not a database, it's a protocol, because all I'm doing is I'm using the strain rates to distort it. And once I have the distorts, I have to reconfigure it. Okay? But nevertheless, even if you count that as a database, I basically need to do 4 databases. And once I'm done that, I can do multi-scale modeling, plasticity, just like that. And I don't have to ever do the databases again. I do them only once. Okay? So how does this look? On the mean field side, we run this a lot of times. Because of the hardening, there is a hardening rate and things like that. So we run different contrast ratios. So basically the important thing there is contrast. And in this particular case, for the partitioning, we are treating each phase as isotropic. Right? Again, full field, we actually account for crystal plasticity. But in this one, we only do isotropic on this side, on the mean field side. So we run a lot of simulations. So each one is a simulation. Each square here is one simulation. But we run a lot. This is what a finite element simulation looks like. The model, you see that, right? I mean, this is exactly what I showed you before. The model looks like that. You build a model, and essentially the model works over thousands of microstructures. But you do it once. You have a model, and the model predicts effective stress. It predicts strain hardening, partitioning, and once you have that, you can build a stress strain curve, right? So if I, for example, if I have a microstructure like this, all I need is partitioning and an effective value, and then I can predict a stress strain curve. But now what I'm saying is, you can make up any way you want. So the 2 answers are, one of them is from the model, the other one is the actual finite element simulation. Okay? But of course, the model is incredibly cheap, half a second, and finite element takes up to 24 hours in this case. Right? So the time differences are incredible. For the accuracy, this is not bad, right? I mean, this you can, and again, we change the volume fractions all the way from 25 to 75%. You can run any model, you can make any one you like, and we'll give you an answer just like that. Okay? Crystal plasticity, this is what, if you insist on doing actual Taylor calculation, this is what you should be doing. Again, we don't want to do that because this is slow part. So we want to run inputs and outputs, collect a lot of data, and just make a database. And turns out this database has 500 terms. But once I have this 500 terms, you can give me any crystal orientation, any slip resistance. You can impose any deformation mode, any crystal orientation, any hardness, and I'll predict this answer just from the database. Okay? How does that look when you actually do this? So this is what a normal Taylor type model calculation looks like. With so it depends on how many terms you use in the expansion. So the other one on the other slide, I had 500, but you can change it. You can have 3,000, you can have 250. Depends on how many you want to do and what accuracy you do. Obviously, the number of terms decreases, the accuracy is worse. As the number of terms increases, the accuracy gets better. Okay? And you can see, you can predict texture, you can predict stress strain curves. And the difference in time is very large, right? So you can do that. Now you can make any texture you like, right? This is not restricted to one particular texture, basically. So we have one database for FCC, one database for BCC. It can be any BCC metal, any FCC metal. It doesn't even depend on that. Okay? And we can match stress strain curves, path changes, right? You put that in Abacus, you can do path changes. You can get final textures that look very good. But again, the calculations are really fast, right? Oops, I went the wrong direction. And the last work now we are doing is FLDs. So we do the same thing, FLDs. So instead of using the real crystal plasticity calculations, we are using the database to compute FLDs. And basically, the cost is only 4%, so the 9.96% reduction in time cost, right? So that's now the third database is localization. Remember, I showed this with isotropic case. But to do this properly, other than localization, you also have to worry about being able to do it for any boundary condition, right? The one that I showed you before was for one boundary condition. If I can only do it in one boundary condition, it's of very little value, right? How will I know what boundary condition is? So it turns out it's very easy, because in this way of thinking, because these kernels now have to be expanded on the boundary conditions, right? And you basically parameterize it. Turns out there's a very smart way to do this. I think the first person to do this was Van Houten in Belgium, Leuven. So that's his idea of how to parameterize this in terms of angles. The advantage of parameterizing this in terms of angles is DFTs work. So once you put it into an angle, you can basically do DFTs, and it's very fast. So once you do that, now I can do this, any microstructure. Now we can put any boundary condition. Before I showed you for only one boundary condition. Now we can do for any boundary condition, any periodic boundary condition. It has to be periodic, okay? Any periodic boundary condition. And then same thing. Now I can get every component of the local strain rate tensor. Every component is there. And you see the MKS result, you see the FEM result. And now basically it works. So now I have the third database, right? I have 1, 2, and 3. Fourth one is not there yet. We are working on this. And this is a distortion one. We are trying to map this. So basically, because I know the local, I know the local velocity gradient, I can recover the velocities. And if I have the velocities, I can distort it. That part is easy. Hard part is to push this back into this geometry, right? Because I'm stuck with DFTs. So it has to look like a uniform cuboidal. So I need to find a way to push this back to that. That's the hard part. So because this is periodic, so this gets repeated everywhere. You can get from here to a rectangle. So this is a square. This is no longer a square. But you can easily make this a rectangle. That part is easy, because it's periodicity. You just pad it in the right place. So now we have to go back from the rectangle to the square. That's the part we are working on. We don't have that yet. Okay, and again, the trick is to do it incredibly fast. If you can do it by interpolation, there are many interpolation schemes you can do that. But again, the geometry itself has changed. Now the periodicity is now on this rectangle, not on the square. So that we have to pay attention to that, and that's where we are working on. We don't have the answer to that yet. But as soon as that is done, then all databases are ready, and we can do this multi-scale modeling much faster than anybody has been thinking of. Okay, I don't know, maybe I got done way fast than earlier. Okay, I guess. I think, yeah, we can talk about other things if you guys want. So when was this supposed to be done? At 4:30? 4:30? Okay. So maybe I went too fast. So essentially, you can read that, but essentially, I hope I convinced you that this is a new way of thinking, and it has merit. It has certainly something that you should think of.
And on one slide you showed the comparison between the Taylor model and your
Okay.
reduced model.
Sure.
And usually the Taylor model is much stiffer than finite element simulations.
Oh yeah.
And in your case, the DFT is
No, there is no finite element here. Both are Taylor model. One of them I'm doing the actual calculations. So, right, the difference is in one case, I'm still assuming that every grain sees the same strain. But in one case, I'm actually solving these equations. In the other case, I'm using the DFTs I already have to compute the functions, right? So that, no, good question, good question. So, yeah, they're both the same, the techniques. So what you're seeing is the error in my DFT representation, because if I use more terms, if I use all the terms, and the number of DFTs is a few million, 200 million DFTs. That's the total. So if I use all of them, I'll basically get the exact answer, because DFTs guarantee you that you'll get the same answer, right? But the amazing thing is that from 200 million, I can come down to, in this case, 255. I can use the top 255 and still get these kinds of answers. All right, go ahead.
But you, if you would use all DFTs, you could use fast Fourier transforms, right? If you don't use with reduced.
That's right. So right now, when we reconstruct, we are not using fast Fourier transforms because there are only 250. Yeah, yeah, absolutely. Right. I don't know if everybody followed what he's saying.
I also thought I use FFT that tries to identify the principal modes.
Hmm.
If I do that, I can't use FFT.
Right.
If
No.
I use the reduced system,
Hmm.
DFT is much slower than using FFT with full system.
So it all depends on how you do the reduced system. That's where it comes down to. That's it comes down to that. So just so that everybody is following this discussion, if I have a discrete set of values, Fi, right? These are discrete set of values. So this is in the real space. So this is S, and this is my Fourier series. This is my frequency space. If I have this and I want all of them, it's very hard to beat the speed of FFT. In fact, there's nothing better than that, I mean, essentially. Because any calculation requires n square. Or if the number of terms here is S, then it requires S square, and FFT is S log S. So it's not even close, especially when S is very large, which it is. In all our cases, S is extremely large. So if I have this and I want to insist on coming back to all of them, then there is no way to beat DFT or FFT. But if I'm only going to use some of them, right? In my example, this column is 200 million. I'm only using 255 of them, the top 255 of them. So the reconstructions, we are doing it basically the brute force way. So we are basically doing the n square calculation. But n square of this is still much smaller than the entire n square, right? So, but it also depends on how you code it. Even there, how you code the 255, yeah. I mean, you may have to talk to some of the students who did this, because I stopped coding about 15 years back. I haven't written a single line of code in 15 years. So, so I forgot all the tricks. The way I usually tell is that when I finished my PhD, so the code that I wrote in my PhD was the first one to do crystal plasticity in a commercial finite element code. So at that point, my coding skills were really very good. Nobody else could beat me. About 10, 15 years after being a faculty member, my codes were still better. But at one point, somebody wrote a code that was much better than mine. And I said, that day onwards, I will not write a single line anymore. That's the end of my coding. So I stopped coding on that day, somewhere around 2010 or 2000, a little bit before that. Anyway, yes, I mean, that's a very smart observation. When you go back from a small list to the big list, you have to do it carefully. Otherwise, you're stuck with the n square problem. Very smart observation. That's very good. Okay. Yeah. So you have to pay attention to a lot of details in this, and of course, what I'm showing you has been optimized the heck out of it. I mean, I don't think you'll find any easy way of optimizing many of these things. I mean, I shouldn't say that, because the programming changes quite a lot. So this was done in 2009, as you can see. So I'm pretty sure things have gotten better since then. So I'm sure the optimization is somewhat better even now. But at that time, it was the best that we could do. Okay. Okay. Any other questions I can answer? Okay. So as I said before, the pymks.org is where we keep all the codes. There are lots of examples. Mine doesn't go because it's not on the internet. I tried to get on EduROM, but I can't get it on there, so I can't see it. But if you go to pymks.org, you should see many of these things there. And feel free to use it and tell us what works, what doesn't work. It's very likely some parts don't work, but let us know. Okay, with that, I'm going to stop. I think this is it. Thank you. Thank you.